Welcome back to Physics 142. In this video, I just want to spend a little time summarizing what we've learned so far about the Biot Savart law, just to make sure that we're all on the same page here. So we've learned that the Biot Savart law tells us how much magnetic field gets produced by a little piece of wire containing a little bit of current that is containing moving charge. So the sort of first example that we did is if we think about having a little piece, just a little piece of wire here with some current in it. So we say the wire has a length, amount of current I, and a length dl. All right, it has current I and length dl. So here's my little piece of wire. And we think about some spot in space that's a distance r away, right? That's a distance r away, all right, from IDL. Then what we learned is that we can find out that the amount of magnetic field produced at this spot, right, a distance r away, the magnetic field produced at that spot is mu naught times the amount of current I divided by 4 pi times dl over r squared. And to get the direction, we always cross with the r hat vector, right? Cross with the r hat vector. And just to remind ourselves, r hat is a vector, a unit vector that points in the same direction as r, right? But it just is a unit vector. It just has length 1. So if we've done this cross product here, right? Maybe we have IDL cross R here, right? IDL cross R. Then in this case, if I'm doing IDL cross R, I would get, point with your finger towards IDL. Goodness, I almost did my cross product backwards. Point along IDL, curl your fingers to the R hat vector, and my thumb would then be pointing up out of the page. And so in this particular example, I would get out of the page, right? Or more generally, we realize that the direction always is just wrapping around our current element, right? So if we point our thumb along the current element and we curl our fingers around it, that shows us the direction of the magnetic field. So we'll say the direction here is around the piece, right? Around that little piece of wire. For this particular one, if we chose an x, y coordinate system, then for this particular one, that would be the k hat direction for that particular spot. All right, good. So that is the magnetic field from a little piece of wire. Now, if we have many little pieces, of course, we want to integrate. We want to add up all of those little pieces of wire. And so we did a bunch of examples of this. And one of the examples that we did was a straight wire, all right? A wire, where we had, a little wire, and we considered a spot that was a distance big R away from that wire. In the example that we did, we had a nice symmetric case, right? We went a distance A above the wire, above the spot, and a distance minus A below the spot. But what I'd like to do is I'd like to, as I summarize this, actually generalize this, and let's just think about a wire where we don't actually have symmetry, all right? Maybe we start at some spot down here, right? And we'll call that spot down here Y1, and we'll go up to some other generic spot here, Y2, and these could be anything. As a matter of fact, we could even imagine just having Y2 end right here, right? Maybe we consider a point off the wire generically, right? So how do we take our result that we had before, our method that we had before, and generalize it to this spot sort of anywhere around the wire? And the answer to that is, well, let's remember the result that we got from the straight wire. If you don't remember the result, I encourage you to go back and look at that video again, all right? But the result that we ended up working out from the Biot Savart law is we got that the magnetic field was mu naught times I times big R divided by 4 pi times this integral, and our limits of integration before were y1 equals minus a and y2 equals a, but now I'm just going to put them in as more generic, y1 and y2, and inside the integral we had a dy over big R squared plus y squared to the 3/2 power, to the 3/2 power. And that 3/2 power came from the fact that when we were considering this distance from y1 to our spot, right, when we were considering that distance, we realized that was the square root of big R squared over, whatever distance from the origin down to y1, right, whatever that ended up being squared, right, that ended up being our distance there, and that also ended up factoring into the trigonometry when we took the cross product, right? The dl times the r hat times the sine phi. We needed to have another factor of this from the sine phi, and that's how we end up getting the 3/2 power. So if you take this integral just more generically then, the result that you end up getting is mu naught times I divided by 4 pi, and you end up with an r on the bottom because you end up with a r squared that comes out and cancels one of those r's, all right? And then we end up just with y2 over the square root of r squared plus y2 squared minus y1 over the square root of r squared plus y1 squared, all right? And so this is just more generic for any two spots, y1 and y2. You can apply it more generally. And I should mention that this formula often then gets written another way, all right? And the way that this gets written is normally we've been thinking about the angle phi between our dl vectors and our r hat vectors, right? That we've always, for the cross products, is the angle between the dl vectors and the r hat vectors that matters, all right? And specifically, it's always been the sine of that angle, which involved this big R here, all right? But interestingly, if we instead take and think about a different angle, if we think about the angles here at the top, all right, these two angles right here, often this will get labeled a different letter, so maybe I'll label this theta and call this theta 2. You can't even read that, but that's theta 2, all right, and this one is theta 1, okay? If we take those angles instead, what you might notice is that we end up getting that these angles, if you took, say, the sine of those angles, you would end up with, looking at this distance here, right, this distance from here down to here, that would be the distance y1, right, and the distance from here to here, that would be distance y2, and that the sine of those angles is actually just this term, that we could write this term as sine of theta 2, and we could write this term as sine of theta 1. And so it's worth noting that a lot of textbooks will actually write the formula in terms of these angles here more generically. They'll write them in terms of those angles rather than in terms of the points y2 and y1. I don't actually really care, it's they're equivalent. It's just good to know that there are a bunch of different ways of writing this formula, sine theta 2 minus sine theta 1. I do think it's a little confusing. These thetas here, though, are not the angle between the DLs and the R hats. They're the other angle, and so that can be a little confusing. They're the angle from the point to the end of the wire, is what those thetas are. Now, so this is the more general case. I mean, if you plug in, minus A and A, then you can plug in A and minus A and get the result that we got last time as well. But it's useful to know about the more general derivation. Then what we said is, well, what if we make this wire really, really long? So we take y2 and we make that go up to be a really big number, and we take y1 and we make that go very, very negative. Then what happens? Well, then what ends up happening is that these r's don't really matter, all right? These r's don't really matter. You end up getting just a factor of 2 out of this term, because this just becomes y2 divided by y2, and this becomes minus y1 divided by y1, which the minus minus becomes a plus, and so this just becomes a factor of 2. Or another way of thinking about it is this theta 1, if y1 gets really, really long, gets closer and closer to 90 degrees. And actually we might think of it then as negative 90 degrees because it's going down here, right? And theta 2, that would go all the way up the other way. That would go to positive 90 degrees. And so that would end up with you just getting 1 plus 1, and this becomes a factor of 2. And so we saw that in the last video as well, but just want to bring that back up. And so the answer for a really long straight wire ends up just being this whole thing multiplied by 2, sort of the maximum you could make this, right? Think about what's the maximum you could make something with 2 sides. Well, the biggest this one could be as 1, and the biggest this one could be as 1. So if you add them together, the max of that is 2. And so this just becomes mu naught times I divided by 2 pi r for a very long straight wire. And remember that it's wrapping around the wire, right? With sort of our, I don't even remember what sort of right-hand rule we're on, right? But if you take your thumb in the direction of the current, your fingers will always wrap around and show you what the B field looks like around that wire. There's a nice figure in your textbook that you can look at for that as well. All right, the last thing is that we mentioned is that if you have more complicated setups, right, that is, maybe setups where you have a bunch of straight wires, maybe you combine them with some curved wires, whatever you want your circuit to look like, all right, you can always approach this problem by dividing it up into more manageable chunks, right? So, something like this, you'd split it up into a bunch of straight wires and curved wires that you could then combine together to get your results. So for more complex setups, right, the key is to sort of use superposition, split into separate curves, manageable curves, and then combine results, right? So find as many sort of straight wires as you can, parts of circles as you can, combine them all together. All right, good. So that is sort of summarizing all the different Biot Savart examples that you've done. There's some good homework problems using Biot Savart that make you think about this and stretch you even a little further on some of this. And just to really make sure you're getting it, I want to give you one more problem, one more example problem. So let me move the board up here. All right, so we'll move the board up. And just one more example for you to think about here, all right, is let's think about an example where you have a wire and a quarter curve like that, and then another wire, right? And we'll run the current through it this way and this way. And I want to know, what about if we choose a spot P, that's a distance big R away from this curve, all right? And that's nicely lined up with these two semi-infinite wires, with these two wires that go really, really far in each direction. What is the magnetic field B at P? All right? And this is a good practice exercise. I'm not actually going to go through it in detail, all right? You should remember that, well, to solve it, you're going to want to break it into 3 separate parts. So I would suggest breaking it into maybe a part for this wire, a part for the half circle, and a part for this wire, right? So 3 separate parts. Remember, one thing that might be worth noting, if I decide to then go back to where I'd start, that would add a 4th part, right? If I instead went and did that, that would add a 4th part, right? And the current would be going the opposite direction. And so that would change the sign of things. So that's just a thing to be aware of. All right. But here we want to split it into 3 different parts, right? So B is going to be B1 plus B2 plus B3. None of those really look like B's. So, you know, be better than Professor Leisman at your handwriting, at least on, you know, your written problems that you have to hand in. But there you go, right? You'll 3 separate B's. You'll want to draw in some DL vectors, right? Think about your DL vectors. Oh, this is black. Well, that's okay. So here's a DL vector, right? Here's a DL vector. Here would be a DL vector, right? And not only DL vectors, right? You're also going to then want to think about your R hat vectors, right? R hat vectors point from DL to P, right? So an R hat vector here, right? An R hat vector would point this way from this one, and here the R hat vector points like that. There you go, R hat. Can barely see that, but that's okay, right? It's perpendicular. And you know, what you'll probably end up finding is that, well, you have these two R hats are going in the same direction, so you'll have a sign of 0 in your equation. So think about what happens there. Here they're going in opposite directions. You'll have a sign of 180, which is also 0, so think about what happens there. And here you have 2 things that are perpendicular on this quarter circle, and so that's going to have a sign of 90. And so I'd suggest trying to work it out. The answer to this problem ends up being, we'll write it down, the answer ends up being mu naught times I divided by 8R, and the direction ends up being into the page. All right? And so if you have any questions on that exercise, you should, you know, try it and reach out to me, right? Remember, you're going to need to write down the Biot Savart law. Oh, this is supposed to be an equal sign. That's not very helpful, is it? The B total is adding up those 3. There we go. So, you know, reach out to me and ask. You'll have to write down the Biot Savart law. You'll write B1, right, is mu naught over 4 pi, and I is constant, so that'll also come out the integral, right? Times the integral of dl cross r hat over r squared. So you'll take this cross product for all of them, and remember that the cross product is always going to be dl times the magnitude of r hat, which is always just 1, all right, times the sine of the angle between them. All right, and so that is going to be that sine of the angle between. That's going to be really key. All right, this will end up giving you a 0 in 2 cases and a 1 in the one other case, and you'll be able to go and integrate from there. You'll note you just have a quarter circle here, and so that hopefully is also helpful in getting to this result. All right, well, there you have it. This hopefully summarizes a lot that we've done with Biot Savart and gives you another little example to practice.